All right, let's talk about improper integrals. 23rd. Improper integrals. And so typically what I point out is that when we talk about improper integrals, we're usually talking about integrals that involve infinity as one of the limits of integration. Now, there actually is a second type, and we'll talk about that briefly near the end, because he did cover that in class yesterday. So, but typically this means involving infinity. Your teacher probably has or will do this example, but it's one that's worth seeing again. So the usual kind of first example is the integral from 1 to infinity of 1 over x dx, which is a definite integral. So even if actually any improper integral is definite, because you're always going to have limits of integration. So if we look at what this looks like, we're thinking about graphing the function 1 over x and finding the area under that function from x equals 1 all the way to the right. We got some more pens here. So we're looking at kind of expressing all of this area. So the way we do this is, since infinity isn't a real number, we can't just plug it in, although people do all the time. I will point out, like, people are gonna say, like, just plug in infinity, you get 1 over infinity, 0, stuff like that. But we're gonna be a little bit more proper because that's probably what your teacher expects. So let me show you like the right way, and then we'll talk about the way people do it. So if I was gonna find this integral, we're gonna rewrite this as the limit as, you can use any letter you like. People usually use a B for an upper limit and an A for a lower limit, although any letter is fine if you haven't already used it. So we're going to write this as the limit as B goes to infinity of the integral from 1 to B of 1 over x dx. Because then we're just pretending like B is some positive real number, and we can evaluate the integral and plug in B just fine. So that's going to be the limit as B goes to infinity. The integral of 1 over x is the natural log of the absolute value of x, evaluated from 1 to b. We don't really need the absolute value here because what we're plugging in is always going to be positive, but it doesn't hurt to write it. So then we're going to plug in our limit of integration. We're going to write the limit as b goes to infinity of the natural log of the absolute value of b minus the natural log of the absolute value of 1. And then I really wouldn't encourage you to write the natural log of infinity. I would say we know what the natural log graph looks like. As the insides go to infinity, the outsides also go to infinity. Right? If you think about the graph of the natural log of x, which looks like this. Sorry, I don't know how, let's see. Here's your y equal to the natural log of x. You can see that, oh yeah, as the x's get bigger, the y's also get bigger and bigger and bigger. So I would just say that this is equal to infinity minus 0. The natural log of 1 is 0, and the natural log of something that's getting larger and larger and larger is also getting larger and larger and larger. So this integral is infinite, which means the area under the curve is infinite. And we say then that the integral diverges. So the area under f of x equal to 1 over x on the integral from 1 to infinity is infinite. And we say, enough room here, we have enough room, yeah. And we say that the integral from 1 to infinity of 1 over x dx diverges. More generally, if this limit that we're taking over here doesn't exist, whether it's infinity or negative infinity, or just doesn't exist in some sort of weird oscillatory way, we're always going to say the integral diverges when that limit doesn't exist. And yes, the limit being infinity does mean the limit doesn't exist. But we need to be more specific about the way it doesn't exist. Let's look at the other kind of classic example of one that does converge. So very similar, the integral from 1 to infinity of 1 over x squared. So we're going to do the same sort of thing. And this is so whenever you have a limit of integration that's infinite, you always have to replace that with some sort of letter, typically A or B. I always like to call these problems. So infinity is a problem. We're always going to replace the problems with some sort of replacement letter. So we're going to write this in the same sort of way. The limit as b goes to infinity of the integral from 1 to b of 1 over x squared. This integral is representing the area under the curve 1 over x squared, which looks pretty similar to the previous one. I'll point out that 1 over x squared gets smaller faster than 1 over x. I've kind of drawn it a little bit dicily there, but we're looking at the same sort of idea. All this forever and ever and ever, where our function is 1 over x squared. So, same idea. After we've written it this way, what I'm really doing here is I'm ignoring the limit. I'm not even looking at that. I'm writing it the whole time in every step, but I'm really just focused on doing the integral. So my next step, I'm going to say, okay, well, I need to write the limit as b goes to infinity, but then I'm just going to worry about anti-differentiating this. So I might take the step to rewrite it as the integral from 1 to b of x to the negative second, so that it's easier for me to see how to anti-differentiate it. Next step, I'm going to write the limit again, just ignoring it, but I know it's there. And then the integral of that's going to be, well, the antiderivative of x to the negative 2 is x to the negative 1 divided by negative 1 from 1 to b. I really, really think it's in your best interest to not use negative powers if you can avoid it. So I would rewrite this as the limit as b goes to infinity of negative 1 over x to the positive first from 1 to b. It's going to be easier for me to see what's happening if I have a positive power typically. And then we're going to plug in our limits of integration, still ignoring the limit, right? We're not looking at the limit until after we've done everything else. So then we're going to have the limit as b goes to infinity of negative 1 over b minus negative 1 over 1. Now, finally, we can say, all right, if you let b get infinitely large, what's going to happen to 1 over b? Well, if the denominator is really, really big, the fraction gets really, really small. So we're going to get 0 minus negative 1, which is going to equal 1. So what we say here is this integral converges, and it converges to 1. So normally we would just write the integral from 1 to infinity of 1 over x squared dx is equal to 1. But when we write this, what we really mean and what we're saying is this means that the integral from 1 to infinity of 1 over x squared dx converges to the value of 1. But if you write this, people will know that you mean this. I would say for improper integrals, it's always a good idea, if you want to be safe, to state whether you're getting convergence or divergence. Even though it might feel obvious, it's still good to write down. Let's look at some more examples, or unless there's questions so far. Okay. Let's look at the following example. Let's say we have the integral from, let's see what it is here. Yeah, I like that one. Okay. From 2 to infinity of 1 over x squared plus 4 dx. Interesting. So 1 over x squared plus 4. I feel like we've seen integrals like this come up a few times. It is an arctangent, but it's not just arctangent of x. I feel like we want to memorize the formula here. I'll point out that if you have the integral of 1 over x squared plus a squared, the antiderivative is 1 over a times the arctangent of x over a plus c. So in this particular example, our a value is 2. We're going to rewrite this as the limit as b approaches infinity of the integral from 2 to b. And I'm going to re-express this just a tiny bit. I'm going to write this as 1 over x squared plus 2 squared, just to make it more obvious to me that I am just using this formula here. So then we still, right? We're just carrying this limit. So I really do think you should carry the limit with you the whole time. Or if you, well, yeah, no, I think you should do it this way. But we can talk about doing it a different way if you prefer. The antiderivative of 1 over x squared plus 2 squared is going to be 1/2 the arctangent of x over 2. Or if you prefer, the inverse tangent. Evaluated from 2 to infinity. Oh, sorry, 2 to what? B. I'm getting ahead of myself, right? I'm trying to plug in the infinity too soon. The b, not an infinity. Then we plug in our limits of integration. It's too bad that these are all called limits, right? These things here are limits of integration, and we're going to take the limit of that at the end. It's unfortunately the names get reused a lot in math. So it's going to be the limit as b goes to infinity of 1/2 the arctangent of b over 2 minus 1/2 the arctangent of 2 over 2. All right. Here's what I wouldn't write. It's probably not wrong to write this, but I don't like writing 1/2 arctangent of infinity minus 1/2 arctangent of 1. People do this all the time. It's not really correct, but it's also totally accepted. But I would kind of skip this and say, well, what's happening to the arctangent function as b goes to infinity? It's a good question. What is happening with the arctangent function as b goes to infinity? Arctangent. Let's take a quick trip over here. What does the arctangent function look like? Yeah, like that. Right? I saw someone draw it. So the arctangent function, if you remember, the tangent looks like this with the vertical asymptotes at pi over 2 and negative pi over 2. It kind of does this deal. And yes, it goes on to the left and the right, repeating. But if you're trying to invert it, we're just taking that middle section and flipping it across the line y equals x, so that the inverse looks like the same thing, except now your y things are x things and your x things are y things. So your horizontal asymptotes come from the vertical asymptotes, and you get a graph that looks like that. So we can see that as the argument of the inverse tangent function gets larger and larger and larger, the output gets closer and closer and closer to pi over 2, which is kind of weird, but it's true. So this here, this limit as b goes to infinity of 1/2 arctangent of b over 2 minus 1/2 arctangent of 2 over 2. I should write 1. Why am I writing 2 over 2? I should have written 1. Oh, well, it's too late. Is going to be 1/2 times, well, the arctangent of b over 2. The argument's getting bigger and bigger and bigger. So the arctangent of something that's getting infinitely large is getting closer and closer to pi over 2. And then the arctangent of 1 is the angle that if you took tangent of it, you would get 1. And that angle is pi over 4. Right, tangent of pi over 4 is 1, so the arctangent of 1 is equal to pi over 4. And then we could simplify this. It's what? Pi over 4 minus pi over 8, so 2 pi over 8 minus pi over 8, which is pi over 8. This one will probably come up, or something like it. People like to ask this question. Questions so far? Questions from the Zoom folks? Okay. I know I've said like a million times, I try not to ask for questions, but clearly I can't help myself, so I'm gonna ask for questions. Let's look at something a little more exciting. Something like, yeah, let's do this. The integral from negative infinity to 0 of x, yeah, x e to the x. Yeah, x e to the x. So this integral is going to require more work. We're going to either need to do a u sub or integration by parts. And typically when I have to do, especially integration, no, either one really, I don't like writing all the stuff every time. So here's how I would approach this. I would do the first thing and rewrite it as a limit. And since we're going to be replacing the lower limit of integration, we typically use the letter A for the lower limit. You could use B if you wanted to, or literally any letter except for X in this problem. Yeah.
So the limit, it doesn't always have to be at the top. Right?
Correct. It does not have to be at the top. You could always rewrite it so it was at the top, but you do not need to. So I'm going to write this in the way I think makes the most sense. The limit is A goes to negative infinity of the integral from A to 0 of x e to the x dx. And I wouldn't do any other manipulating. Now, here's the issue. I know this integral is going to require integration by parts. And I don't want to write all of this while I'm doing the integration by parts, where I'm doing the uv minus the integral of v du, especially because like a definite integral of integration by parts, I just don't like writing all that stuff. So what I would do is off to the side, I'm just going to do the indefinite integral of x e to the x. So I'm going to let u equal x, and my dv is going to be the rest. And in case I haven't made it clear, the reason I'm picking u equal to x here is because of the late acronym, right? If we are going to try to figure out what we're doing in an integration by parts problem, I'm first trying to pick u equal to a logarithm. If I don't have a log, then any power of x, which is what I picked here, x to the first, then a trig if I don't have either of those, and then almost never an e to the x. All right, so then we get our du equal to 1 times dx. Our v is going to be the antiderivative of e to the x, which is also e to the x. And then we're going to rewrite this as being equal to our u times our v minus the integral of our v times our du. And this is kind of the reason why I don't want to do it with all that. I don't want to have to write like from a to 0 here and from a to 0 here and the limit in front of it. It just seems like a lot to keep track of. So then we finish this off. We get x e to the x minus the antiderivative e to the x is e to the x. I don't need to worry about the plus c here. So what I'm going to do is I'm going to take that, and in the next step here, I'm going to write, this is going to be the limit as a goes to negative infinity of my antiderivative x e to the x minus e to the x from a to 0. And that just feels like a better way to do it to me. Okay, now we're going to plug in. We're going to get the limit as a approaches negative infinity of 0 times e to the 0 minus e to the 0 minus a times e to the a minus e to the a. Now we have to evaluate this limit. 0 times e to the 0 is 0. E to the 0 is 1. So what I have here is the limit is a goes to negative infinity of negative 1 minus a times e to the a plus e to the a. What's happening to e to the a as a goes to negative infinity? This is where I think about the graph. So I think about the graph of y equals e to the x or e to the a. If your input's going to the left to negative infinity, the graph is getting closer and closer and closer to 0. So we can say that this part here is going to get closer and closer to 0. What about this part here? A times e to the a. Ugh. So specifically for the limit, a goes to negative infinity of a times e to the a. A is going to negative infinity and e to the a is going to 0. And infinity times a 0 is an indeterminate form. So there's a couple ways to deal with this. Here's how I would encourage you to think about it. I'm going to rewrite this as the limit as a goes to negative infinity of a divided by e to the negative a. Now I have an infinity over infinity. Top's going to negative infinity, the bottom's going to positive infinity. One of those things is getting bigger a lot faster than the other one. If you graph y equals x versus y equals e to the x, one of those things grows much, much, much faster, the e to the x thing. So some people like to just say, well, the bottom's really a lot bigger than the top, and the limit of this is going to be 0. The other way to do this, which I imagine Dedel would probably expect people to do, is to use L'Hopital's rule. Say, oh, I have an infinity over infinity type. I can use L'Hopital's rule and take the derivative of the top and the derivative of the bottom and get that this is going to be the limit as a goes to negative infinity of the derivative of a is 1. The derivative of e to the negative a is e to the negative a times negative 1. And now we have something where the top is 1 and the denominator is getting infinitely large because e to the negative infinity is e to the infinity, which is really, really big. And 1 over a really big thing is a really small thing. So then we can say that this part is also going to go to 0. And so we're left with negative 1. So we say this interval converges to negative 1. Yeah. Right. So I took my a times e to the a and saw that I have what's called an indeterminate form. So I have something where this is going to negative infinity, and this part here is getting closer and closer to 0. And a 0 times infinity is one of those things that can end up being anything. And so I knew I needed to write it in a way where it was easier for me to compare like what they're both doing. So I said, well, I want to write it as a fraction, and usually you want to bring down the thing to the bottom that's going to be less terrible, for lack of a better word. So I said, well, if I bring e to the a down to the bottom, it's just going to be e to the negative a. And that way I can then think of it, oh, well, the top part is going to a negative infinity, and e to the negative infinity is going to a positive infinity. So that's why I did that. It's not, it's still the same thing. E to the a is equal to 1 over e to the negative a. They are actually the same. So yeah, I'm not changing anything. I'm changing it in that I'm rewriting how I'm expressing it, but I'm not actually, it's not a different thing. It's just expressed differently. Yep. I would say, so there's a lot of indeterminate forms. The ones you probably need to worry about for these kind of integrals are the following. So indeterminate forms we should look for indeterminate forms that might pop up in these improper integrals are 0 over 0, infinity over infinity, or infinity times 0. There are other indeterminate forms, but these are the ones you're likely to see if you're dealing with an improper integral. And when I say infinity, I mean plus or minus infinity. So either of these infinities can be positive or negative. That infinity can be positive or negative. We just don't typically write it that way. Good questions. Let's look at another example. Let's say we want to find the integral from negative infinity to infinity of 4x cubed times e to the negative x to the 4th. So whenever you have an integral from negative infinity to infinity, you have two problems, infinity and negative infinity. And the thing about improper integrals is we can only deal with one problem at a time. So we have to break this up somewhere in the middle. You can break it up anywhere. And in fact, there's a homework problem asking you to show that it doesn't matter if you pick an A or a B to break up an integral from negative infinity to infinity, you're still going to get the same result. Typically, we pick 0 to break it up at, unless there's a good reason to pick something else. So I would break this up as the integral from negative infinity to 0 of 4x cubed times e to the negative x to the fourth, plus the integral from 0 to infinity of 4x cubed times e to the negative x to the fourth. And we're going to deal with each of these separately. And it's good to know that if one of these two integrals that I've written over here diverges, we're done. The whole thing diverges. We don't even look at what happens with the other piece. Unless someone asks you how it diverges, which we're not typically going to do. But usually once one piece is divergent, you're done. Now, if one piece converges, then we have to look what the other piece does. Because if they both converge, then they add up to whatever the convergent value is. But if one of them diverges, then the whole thing diverges to either infinity or negative infinity or something like that. So let's see here. I'm going to look at the one with the positive infinity first. So I'm going to say that this integral here, the integral from 0 to infinity of 4x cubed e to the negative x to the fourth dx is going to be the limit as b goes to infinity of the integral from 0 to b of 4x cubed times e to the negative x to the fourth. I'm going to actually do the actual anti-differentiating off to the side here. So if I was trying to do the antiderivative of 4x cubed e to the negative x to the fourth, it might be a u sub, it might be integration by parts. Think about it for yourself for a second. What do you think it's going to be? I see a pretty good candidate for a u substitution. I would be letting u equal negative x to the fourth. You could also pick positive x to the fourth if you preferred. Either way is fine. My du is going to be negative 4x cubed dx. So negative du is equal to positive 4x cubed dx. And I'm pretty pleased about that because I exactly have a 4x cubed dx. So I can rewrite this integral as the negative of the integral of e to the u du. So there's my negative du, which is my 4x cubed dx, and there's my e to the u, which is my e to the negative x to the fourth. So that's great. That's going to be negative e to the u, which is negative e to the negative x to the fourth. So when we then take that down here, we're going to get the limit as b goes to infinity of e negative e to the negative x to the fourth evaluated from 0 to b. So figuring out what we've got here, we've got the limit as b goes to infinity of negative e to the negative b to the fourth minus negative e to the negative 0. All right. How do I want to say this the right way? I don't love e to the negative infinity. It's not something that's ever stuck in my brain well. Sticks in your brain, great, do it that way. But I almost always have to rewrite this in a way so that I have a positive exponent because it just makes more sense to me that way. So I would write this as, or rewrite this as the limit as b goes to infinity of negative 1 over e to the positive b to the fourth plus 1. Because to me now it's easier to see what's going on. B is going to infinity. Infinity to the fourth power is still infinity. And e to the infinity is still very, very large, infinity. And then 1 over infinity is small, 0. So that's going to go to 0. We're going to get 0 plus 1, which is 1. Or if you prefer, and it's totally fine, if you can see this and be like, oh yeah, I have infinity to the fourth is infinity, and then negative infinity is my power, and e to the negative infinity is like the left side of the e to the x graph and gets closer and closer to 0. That's also a fine way to view it. It's just not the way I like to view it. So since this converged, we have to look at the other half. Well, looks like it's snowing outside, kind of. Or look behind, like there's like all the little flowers. Anyway, sorry, I was like, oh, kind of looks like snow. Okay, so the other side. The nice thing about the other side here is we've already done most of the work. So for the other half, the integral from negative infinity to 0 of 4x cubed e to the negative x to the fourth dx, we're going to get the limit as a goes to negative infinity of our antiderivative, right? We don't need to write the integral again. Let's just write the antiderivative, which is negative e to the negative x to the fourth from a to 0. Plug in the limits of integration. We get negative e to the negative 0 is just 0. And then minus negative e to the negative a to the fourth. And here's where you have to be extra careful, I think. A is going to negative infinity. Negative infinity to the fourth power is positive infinity, but then there's a negative in front of that, turning it back into a negative infinity. So this is still going to be an e to the negative infinity, which is going to 0. Or if you're like me and you don't want to think about it that way, you can write it as the limit as a goes to negative infinity of negative e to the 0 is -1 plus 1 over e to the positive a to the fourth. And then negative infinity to the fourth power is positive infinity, and e to the infinity is big. So 1 over a big thing is small, and you get -1 plus 0, which is -1. So they both converge to 1 and -1 respectively. And so the whole integral converges to the sum of those two things, which is 0. So the whole integral from negative infinity to infinity of 4x cubed e to the negative x to the fourth dx converges to 0. Which might not be super duper surprising if we notice that the function we started with is an odd function. And so you've got this left half and this right half kind of balancing each other out, canceling, I should say canceling each other out. Right, if you graph this, in fact, yeah, let's graph it. I'm not going to graph it because why would I graph something that I'm not good graphing? We graph y equals 4x cubed. I know you can't see it yet. Just give me a second. E to the x to the fourth. That. Maybe why don't you go there? I did that on my laptop. My laptop's not connected to the screen. Sometimes. Sorry, 1 second. Let me actually try to show you the thing I wanted to show you because I think it's neat. Sorry about that. In my other classes, I'm on my laptop teaching from, so it makes more sense that I would do that. But here we go. So y equals 4x cubed times e to the negative x to the fourth. Yeah, cool. So here's what this graph looks like. Oh, sorry, 1 second. There you go. So you can kind of see, oh yeah, look, those areas are totally canceling each other out. The area over here is literally +1 from 0 to infinity. And the area to the left from negative infinity to 0 is -1, and they add to 0. Which actually brings up something. Oh, actually, so there's a question there, sorry. Wouldn't it be -1 as well for the positive infinity one? It would not be -1 as well. Let's go back and take a look. So we look back at the work we were doing for the positive infinity one, it ended up being 0 minus -1, which is going to be a 0 plus 1, which is +1. So definitely 1 for the positive infinity one. This actually brings up an interesting question though. Does that mean that if your function's odd, the integral from negative infinity to infinity will always be 0? And the answer is no. The answer is actually yes, if it converges, and no if it doesn't. So here's what I mean. If we look at this integral for a second, the integral from negative infinity to infinity of x cubed. Definitely an odd function. Certainly something like the integral from -10 to 10 of x cubed dx would be 0 because the left-hand side and the right-hand side would cancel each other out. Right, looks kind of like, my picture is never good for this. It looks kind of like that. So if you were going from -10 to 10, you say like, oh yeah, this area here and this area here, those are exactly going to add it to 0. The problem is when it's infinite, if one side diverges, you're done. The whole thing diverges. And if you break this up as the integral from negative infinity to 0 of x cubed dx, plus the integral from 0 to infinity of x cubed dx, and then look at this right-hand side first, well, then the integral from 0 to infinity of x cubed dx is equal to the limit as b goes to infinity of the integral from 0 to b of x cubed. We anti-differentiate because the limit as b goes to infinity of x to the 4th over 4 from 0 to b. We plug in and we get the limit as b goes to infinity of b to the 4th over 4 minus 0 to the 4th over 4. And as b goes to infinity, b to the 4th certainly goes to infinity, which means it diverges. And we don't even think about the fact that the other part's going to be negative infinity. So this integral diverges. And yes, I really understand the desire to want those two areas to cancel each other out and get the answer to be 0. This is not the case. Because this other part diverges to negative infinity, and infinity plus negative infinity is an indeterminate form. And there's no way to deal with it to show that it would be 0. Even though we really, really, really like it to be. I would like it to be too. Like, don't get me wrong, I feel like this interval should be 0. It's not. It's divergent. What else did I have on my agenda with these improper intervals here? Look out, see that one. Time is it? Okay, we got time. So let's look at one more of these types. Let's say we have the integral from e to infinity of 1 over x times the natural log of x dx. So here's what we're going to do. We're going to start off in the usual way. We're going to rewrite this as the limit as b approaches infinity of the integral from e to b of 1 over x natural log of x dx. I see a function I don't know how to anti-differentiate right off the bat. So before we go any further with this limit, I want you all on the side to try to find the antiderivative of 1 over x natural log of x, either by doing a u substitution or an integration by parts. And you all should be trying to do that right now. I think you should get the natural log of the natural log of x if you've integrated this, anti-differentiated this correctly. Well, let's take a look and see. I was trying this. I would try u sub first, because usually I would try u sub first, right? I always feel like it's going to be easier to try u sub first. And then my du is going to be 1 over x dx, and I'm pretty happy about that because I have a 1 over x. So I'm thinking of this integral as 1 over natural log of x times 1 over x dx. There's my du. Here's a 1 over u. So my integral becomes the integral of 1 over u du, which is the natural log of the absolute value of u By the way, you only get the absolute value when you've integrated 1 over whatever, 1 over u, 1 over x. That's when you get the natural log of that x or that u. But then when I plug back in the natural log of x my u, it's just a regular natural log of x. So I'm going to get the natural log of the absolute value of the natural log of x. And that's what's going to go into my integral right over here. So I'm going to have the limit as b goes to infinity of the natural log of the absolute value of the natural log of x from e to b. Do that, limit as b goes to infinity of the natural log of the absolute value of the natural log of b minus the natural log of the absolute value of the natural log of b. All right. As b goes to infinity, what happens to the natural log of b? It also goes to infinity. And then if the natural log of b is going to infinity, then the natural log of that is also going to infinity. Really, really slowly. Like if you were to graph the natural log of the natural log of x, it might look like it was just a flat line, a horizontal line, because it just grows so gradually. But it does grow, and it does get larger and larger and larger forever and ever and ever. It goes to infinity. This is going to be infinity minus, it doesn't really matter, but that is the natural log of 1, which is 0. So this thing diverges. Yeah. Want to look at one more of this type of improperness or impropriety? Yeah, sure. Because I want to point out one other thing. So let's look at one more where we have split it up. Let's say we have the integral from negative infinity to infinity of, sure, x squared times e to the negative x dx. So this one, I'm going to break it up because I have to. I don't have any choice. I'm going to break it up at 0. I'm going to do the integral from negative infinity to 0 of x squared e to the negative x dx plus the integral from 0 to infinity of x squared e to the negative x dx. What I really want you to see with this one is if you have to break it up into 2 pieces, you want to try to deal with the piece that you think might diverge. Because if you get the one that diverges and you do that one first, then you don't have to look at the other one at all. So I can look at both of these, and I'm pretty sure that of the 2 of these, this one is more likely to diverge. Question. Exactly what I was about to say. So the way I know is that here I'm going to let my b or my a or whatever go to negative infinity. And e to the negative infinity is infinitely large. So this function, as I go way to the left, I'm getting something like negative infinity squared times e to the infinity, which is going to be super duper huge. The fact that this function itself is getting very, very large is a good indicator that the area underneath it is also going to be extremely large. On the other hand, the right-hand side here, x squared times e to the negative x as x goes to positive infinity. Yeah, the x squared is getting big, but the e to the negative infinity is getting really, really small. And if you actually graph this function, y equal to x squared e to the negative x does look something like this. It's something kind of like, it's kind of like that. So certainly of the 2 sides, it seems a lot more likely that the area under the left side is going to be divergent versus the area under the right side, which may or may not be divergent. So if you have a good intuition about which side might, or which piece might be the divergent piece, do that one first, because you're cutting the work you have to do. It's still kind of a bear though. So if I was going to do this, it would be the limit as a goes to negative infinity of the integral from a to 0 of x squared e to the negative x dx. And this is where I would employ tabular integration. So I'm going to let my u be x squared, and then I take all my derivatives. My dv is e to the negative x. All my antiderivatives, the next one's negative e to the negative x, and then positive e to the negative x, and then negative e to the negative x. And then it's a plus minus plus minus plus minus plus. So it looks like all my terms are actually going to end up being negative. So it's going to be x squared times negative e to the negative x minus 2x times e to the negative x plus 2 times negative e to the negative x. So what we're going to get here is we're going to get the limit as a goes to negative infinity of negative x squared times e to the negative x minus 2x times e to the negative x minus 2 times e to the negative x from a to 0. We're going to plug in, and the limit is a goes to negative infinity of 0 minus 0 minus 2 times e to the 0 minus, well, I might just change that to a plus and distribute the minus sign. No, it's too late. So minus a squared e to the negative a minus 2a e to the negative a minus 2 e to the negative a. But look at what's happening here. If a is going to negative infinity, then e to the negative a is going to infinity. So this part is going to infinity. And this part is going to negative infinity, but it's a negative infinity. And this part's going to some other, right? It's getting infinitely large or negative. It's some sort of divergence. The way you can maybe make this a little bit easier to see what you've actually got is you could think of it as just, if you factor out the e to the negative a, it's going to be really the limit as a goes to negative infinity of, I don't really care about this negative 2, but it's there. Negative 2 plus e to the negative a times a squared plus 2a plus 2. And this part is going to infinity. And all of this is also going to infinity. And infinity times infinity is infinity. So this thing diverges. Bless you. I saw an interesting, I was looking at the Temergali of this class, one of the practice midterms or the actual midterm she posted last quarter. And there was one question on there that I thought was kind of interesting. She wrote, and it's germane to what we're doing here. The thing she wrote was essentially, what do we mean when we write e to the negative infinity is equal to 0? I thought this was a good question. It made me think a little bit. Because what we really mean here is we don't actually mean you're plugging infinity. What we really mean is the limit as x approaches negative infinity of e to the x is 0. That's what we really mean by something like that. Or you could also phrase it as the limit as x approaches positive infinity of e to the negative x is equal to 0. That's all we mean, is that x is getting either larger and larger and larger, e to the negative x is getting closer and closer and closer to 0, or as x is getting negatively large, e to the positive x is getting close to 0. We're just talking about the behavior of a graph when we talk about when we write something like this. So someone said in the chat here, I thought e to the negative infinity was 0. I wouldn't say that exactly, right? It's not really correct because again, you can't really plug in infinity actually, right? If I said my function f of x was 1 over x, it's really not correct to say that f of infinity equals 1 over infinity equals 0. That is, although the idea is right, is not what I would say proper math. Now, do people do improper math all the time? Yes, people do improper math all the time. That's totally okay. But if you're writing this, you need to understand what it means. And the meaning isn't that 1 over infinity is equal to 0. The meaning is that the limit as x approaches infinity of 1 over x is 0, meaning the function never actually equals 0. It just gets really close to, how close to 0? As close to 0 as you want if you go far enough out. So that's what we mean when we ask this question, right? We're not actually getting a value of 0. We're getting that this function gets closer and closer. Same deal here. this e to the negative infinity being 0 really means that the function, you can either think of it either way, but e to the negative x gets really close to y equal to 0 as x goes to infinity. Oh, no. So for the previous example, sorry. The previous example, I don't believe so because, right, so you said we don't have e to the negative infinity in this example. We have e to the negative infinity. And e to the negative infinity is e to the infinity, which is going to get infinitely large. That's what's happening here, right? A is going to negative infinity, and I have e to the negative a. That's what's happening there. Cool. All right. Let's see. Keep things in order here. All right. So that's most of improper integration. Except I saw that Dedell did an example yesterday of the other type of improper integral, which I don't think there are any homework problems on, because I don't think your textbook has any improper integrals that aren't infinity or negative infinity types. But let's look at one example of the other type of improper integral, just because we should mention it. So the other type of improper integral is when you don't have an infinity or infinity, negative infinity or infinity, but you have a definite integral where the function you're integrating is undefined somewhere on the integral. So for example, someone could ask, what's the integral from -1 to 1 of 1 over x squared? Which looks perfectly innocuous. If you weren't paying attention, it'd be really, really easy to incorrectly get the wrong answer here. If you didn't notice this, you might be like, well, sure, I can integrate that. It's going to be -1 to 1 of x. Don't write this down, by the way. What I'm writing down, or what I'm writing down now, is wrong. So be aware of that. I'm going to scratch that in a minute. That's going to be, let's see, the antiderivative of x to the -2 is x to the -1. So it's x to the -1 divided by -1. From -1 to 1, that's going to be -1 over x from -1 to 1, which is -1 over 1. Minus -1 over -1, which looks like -1 minus 1, which is -2. Which is really weird that the answer would be -2, because the area under this function, which is always positive, should be positive. There's a problem here. And the problem is that this function is undefined on this interval. It's undefined at 0. This region that we looked at looks like this. If we go from -1 to 1, we're trying to capture all this area here and all this area here. Which certainly, if it converges, should converge to something positive, because the area is above the x-axis. So the fact that we got a -2 here feels extremely wrong. So here's what we have to do. If you have a definite integral and the function you're integrating is undefined somewhere on your interval, you have to break it up at that point, if it's not one of the endpoints. So here, we would rewrite this integral from -1 to 1 of 1 over x squared as the integral from -1 to 0 of 1 over x squared, plus the integral from 0 to 1 of 1 over x squared. And then we would deal with each piece separately. Let's deal with the piece that has the positive parts first, because it feels easier. So we're going to rewrite the integral from 0 to 1 of 1 over x squared dx. Well, just like before, when infinity was a problem, we replaced it with an a or a b. Now the 0 is the problem, so we're going to replace it with an a since it's in the bottom. So I'm going to rewrite this as the limit as a approaches 0 of the integral from a to 1 of x to the -2. Yeah, so someone asks, should we always check if functions are defined on the intervals then? And the answer is yes, but like it should be a quick check. We really are just looking like, are you accidentally getting division by 0? For definite intervals. But really it'll probably pop, well, no, I could see being tricky kind of on purpose by asking like, here's all these definite integrals, and then find them, and one of them sneakily being an improper integral. That doesn't seem very kind, but someone could do that. I don't really expect that, but I'm not a student, so what do I know? But looking here, there is one more thing to be slightly aware of here. So if we're between 0 and A, sorry, 0 and 1. So if we're between 0 and 1, so we're living in between 0 and 1 because we're integrating from 0 to 1. What side of 0 are we on? The left or the right? The right. So we should be approaching 0 from the right. And that's always the case when you have one of these. If you're breaking it up, you do want to be approaching your number from the appropriate left or right-hand side. So here we do this, we get the limit as A approaches 0 from the right of the integral of x to the negative second. I'm not going to write x to the negative 1 over negative 1. I'm going to simplify it and write it as negative 1 over x because that is the better way to write it. Just better. Not even maybe you prefer this or that. No, this is the better way to do it. Unless you like doing it the other way, that's fine too. And then you plug in your limits of integration. You get the limit as A approaches 0 from the right of negative 1 over 1 minus negative 1 over A. And then you can see that as A goes to 0, 1 over A is going to diverge to infinity. So we're going to get negative 1 plus infinity, which is just infinity. So this integral diverges. And we don't even need to look at the other half. Question? It's not 0. 1 over A, if A is getting really, really small, right. So this integral diverges. I will point out if you had looked at the other side, if you had done the limit as a B approaches 0 of the integral from negative 1 to B of 1 over x squared dx, we should write the limit as B approaches 0 from the left-hand side. Because if you're between negative 1 and 0, you're on the left side of 0. Again, not super duper important, but it is a little bit important. And again, probably not really that important because again, I don't think, at least in the textbook, that there are literally any improper integrals of this type. I looked. There aren't any in section 5.8. So unless you're going to get some extra homework problems somewhere else, I don't know where you're being asked to do integrals like this. Now, there could be some web work ones in Tempergalley class, which I haven't looked at, so I'll look to see if there are any there. How do we know it's from the right? Because if you're doing the integral from 0 to 1, we're between 0 and 1. And if you're between 0 and 1, you're on the right side of 0 or the larger side of 0. That's how I know. So basically, if it's the lower limit, you're approaching it from the right because you're bigger than it. And if it's the upper limit, you're approaching it from the left because you're less than it. That's the way I'm kind of thinking about it. Let's look at one more. I know I said one, but let's look at one more because it's nice to see one that converges. I feel like there's a question over there.
So how did you get, I just like what's on the graph, but whenever A was just by 0 from the right side to.
So A is going to 0. So A is really, really small. What's a really small number? Like 1 over 1,000, right? 1 over 1,000 is tiny-ish. But then I'm doing 1 divided by that. What's 1 divided by 1 over 1,000? Right, it's getting really big. So the thing is, when A is getting really, really, really small, 1 over A is getting very, very, very large. So that's why I'm getting an infinity here, because this part's just negative 1 and this part's really, really big. The way I always think about fractions is you have reciprocal or inverse relationships. If your denominator is big, your fraction is small. If your denominator is small, your fraction is big. Well, it depends on what the variable is doing, right? Because we just said previously, right? Here, you have a variable in the bottom, but since the variable is getting really, really big, the fraction is getting very, very small. Whereas, if we said the limit as x approaches 0 from the right of 1 over x, then that limit would be positive infinity because you've got a very, very small number and then you're doing 1 divided by that and it's getting very, very large. But this is what I kind of mean. This sort of fraction has the inverse relationship to what's being input. You input a large thing, you get out a small thing. You input a small thing, you get out a large thing. And that's typically true with fractions. If the denominator is, if whatever the denominator is doing, the fraction is doing kind of the opposite of that as far as big versus small. Someone asks, how are we going to zero from the right side if a is the lower limit? Because again, right, if we're between 0 and 1, right, the 0 is the lower limit. And if you're between the lower limit and the upper limit, you have to be bigger than that lower limit, which means you're on the right side of it. All right. Let's do one more example, and then we'll move on to talking about area stuff. Let's say we want to do the integral from, let me make up limits of integration in a second, of 1 over the square root of x minus 4 from 4 to, sure, 13. So this problem is slightly less terrible in that you don't have to break it up, right? The problem point is 4. So if you plug in 4, 4 minus 4 is 0, square root is 0 is 0, and 1 over 0 is, oh, unfortunate, undefined. So we're going to rewrite this as the limit as a approaches 4 from the, you figure out what side of the integral from a to 13. And I'm going to rewrite my integrand instead of as 1 over the square root of x minus 4 as x minus 4 to the negative 1/2 power. All right, so if I'm between 4 and 13, I'm definitely going to be bigger than 4 if I'm between 4 and 13. If I'm bigger than 4, I'm on which side of 4? The right side of 4. I think we can do this in, oh, question. Sure. So let me, well, so actually here's a real issue with this one. We really can't be on the left side of 4. Well, what's 3 minus 4? Right, -1, and the square root of a negative is not defined. So here you absolutely have to be on the right side of 4 because of the type of function we have. But if, for example, you had something like the integral from 1 to 8 of 1 over the cube root of x minus 8, then you would rewrite this as the limit as b approaches 8 of the integral from 1 to b of x minus 8 to the negative 1/3. And then we would be approaching 8 from the left. Because if we're between 1 and 8, we are smaller than 8. And what I've seen over the years is generally true, is that if it's the lower limit you're replacing, you're approaching it from the right. If it's the upper limit you're replacing, you're approaching it from the left. And it's okay to approach from the left here, because a number smaller than 8 minus 8 is negative, but a cube root of a negative is totally okay. So back to this one, I think we can anti-differentiate this without doing a u sub. The antiderivative of x minus 4 to the negative 1/2 is going to be, we still have the limit as a approaches 4 from the right. X minus 4 to the negative 1/2, we're going to add 1 to the power and get x minus 4 to the 1/2 divided by 1/2 or times 2. And since there isn't any coefficient of x, that's it. And you can check, the derivative of this would be 2 times 1/2 times x minus 4 to the negative 1/2 times 1. From a to 13. Then we plug in, we get the limit as a approaches 4 from the right of 2 times 13 minus 4 to the 1/2 minus 2 times a minus 4 to the 1/2. And then here we actually can plug in a, right? It's not like we're trying to plug in infinity and getting a 1 over infinity equal to 0. We can say, well, if I plug in, I've got 2 times 13 minus 4 is 9 to the 1/2 minus 2 times, if I plug in a equal to 4, you got 4 minus 4 to the 1/2. 4 minus 4 is 0, and 0 to any positive power is still 0. So this is just going to be 2 times the square root of 9 minus 2 times 0, which is going to be 6. So this integral converges. to 6. Yeah. Go ahead. Sure. So I was using the anti-power rule, and I was saying that my antiderivative of x minus 4 to the negative 1/2 is going to be x minus 4 to the negative 1/2 plus 1 divided by that new power. But then I skipped writing that and wrote it as 2 times x minus 4 to the 1/2. Question? Why did I pick 4? Excellent question. So if I plug in 4 here, what do I get? Well, I get a 0 where? And 1 over 0 is, well, sometimes yes, but more generally 1 over 0 is undefined. That's why I picked the 4 here. That's why I picked the 8 here. So whenever you've got a definite integral where you might have to use an improper integral technique, it's because one of the values in your interval of integration is making the function undefined. So for example, we're not going to finish this one, but I'll point out that if we did say the limit, sorry, not the limit, the integral from 2 to 7 of 5 over x minus 2 to the third, what's the problem point here? Show me on your fingers. What value of x is a problem for this function? But I should say, what value of x makes this integrand, this function, undefined? Right, 2. So that's why we're going to replace 2 and write it as the limit as a approaches 2 from the right of the integral from a to 7 of 5 over x minus 2 cubed. Someone asked, can we solve the previous one as a normal definite integral? And the answer is, so the question really here is like, could we just have integrated this and then plugged in? And the answer is yes, because it converges. But you don't know it converges until you've actually done the work. Whereas in this next one I wrote, you can't just do this one as normal because it's going to diverge. So really the answer generally is no, you can't, because you don't know if it's going to converge or diverge until you've done it. So you really do need to use the limit. And I know we said we didn't do this one, but now I want to show you that this one diverges. So just to point out, if we rewrite this one, it's the limit as a approaches 2 from the right of the integral from a to 7 of 5 times x minus 2 to the negative third. We're just going to use the anti-power rule here. We're going to get the limit as a approaches 2 from the right. The integral of 5 times x minus 2 to the negative third is going to be 5 times x minus 2 to the negative second divided by negative 2 from a to 7. Here's where I think you need to be a little bit extra careful. So the limit is a approaches 2 from the right. I don't like negative powers, but I'm going to leave it as a negative power to show you. I'm going to have 5 times 7 minus 2 to the negative second over negative 2 minus 5 times a minus 2 to the negative second over negative 2. Now, if you plugged in 2, what's 2 minus 2? What's 0 to the negative 2? Undefined. Because 0 to the negative second power is like, or is the same as 1 over 0 squared. And 1 over 0 squared is 1 over 0, which is undefined. So I really prefer to write this as, say, the limit as a approaches 2 from the right of, I would write this as negative 5 over 2 times 7 minus 2 to the positive second minus negative 5 over 2 times a minus 2 to the second power. And then when I plug in 2, oh, I'm getting 0 in the bottom, and dividing by 0 is undefined. So this is going to diverge, probably to positive infinity. I don't really care. It diverges. Correct. Because again, if I'm on the number line and I'm between the numbers 2 and 7, right, and it's a hard kind of cutoff there, what side of 2 am I on? Exactly. That's how I'm approaching 2 from the right. You're welcome. All right. I always, there's never as much time as I want there to be. Let's move over to the last 8 minutes. Talk about area for just a second. So let's say we want to find, well, that's not the right pen. We want to find the right pen. We want to find the area between y equal to x squared minus 2x and y equal to 3x. And the first thing I'll say about this is when you're finding the area between curves, it's usually a good idea to graph them. You don't always have to graph them. Sometimes you really do need to graph them though to see what region you're looking at. Here is an example where you could get away without graphing. So we'll talk about doing it. No, I want to graph it first, but we'll talk about at the end how you can do it without graphing it. So I'm going to graph these 2 functions. Y equals 3x is just a straight line going through the origin. It's going to look something like this. I know that's not exactly what it looks like. I know it'd be more steep, that I'm trying to draw it in a way so we can see what's going on. And y equal to x squared minus 2x is an upward opening parabola. You might factor it as x times x minus 2, which is either the intercepts are going to be 0 and 2. 1, 2, 3, sure. So there's my parabola intercepts, and it's going to look something like this. It is upward opening. Sure. Again, it doesn't have to be perfect. I'm just trying to make it look kind of nice. So we can see from our graphs that these 2 functions intersect in 2 different points. One of them is clearly the origin, and then we'll find the other one in a second. But we're trying to find this area. So the idea is going to be that we're going to add up areas of rectangular strips. What was the word you used in class? Or cross sections, rectangular cross sections. Either way, cross sections, I'll say cross sections, I'll say strips, I'll say rectangles. But we're just going to say we want to add up all of the areas of these little rectangles or cross sections. So the area of a cross section, aka a rectangle. Well, we know how to find the area of a rectangle: base times height, or height times base. And the height of this rectangle, let's look at this one specifically. The height of this rectangle, where if you're going to find the height of something, it's the top value minus the bottom value. So the height of this rectangle here is the top function minus the bottom function. So our height in this particular example is going to be 3x minus x squared minus 2x. And the base of this rectangle, well, this rectangle is not very wide. It's got a very narrow base here. I'm going to call that base dx, a small change in x. You can call it delta x if you prefer. I really prefer dx because I know I'm going to write an integral at some point. So my area here is going to be the height, which is 3x minus x squared minus 2x times the base, which is dx. But that's just the area of one cross section. I want to add up the areas of all the cross sections. So what am I going to do? Well, I'm going to integrate, because essentially I'm not actually going to write it, but we're taking the sum of all the areas of the rectangles and taking the limit of that sum, which is how we define the integral. So that's the area of one cross section. The total area is going to be the integral of, or I should say the adding up of all the areas. Now, the question we still have to answer is, how far left and how far right can I draw a rectangle or a cross section? Well, I think it's obvious maybe that we can go as far left as 0. But this right-hand point, we actually have to find by setting the two functions equal to each other and see where they intersect. So to find the point of intersection, we're going to just solve the equation x squared minus 2x equal to 3x. We're going to subtract 3x from both sides and get x squared. Negative 2x minus 3x is minus 5x equal to 0. We're going to factor out an x. We're left with an x minus 5. So we get x equal to 0, which we already were pretty confident about. We also get x equal to 5. And if you plug back in 5 to either function, 3 times 5 is 15. Or 5 squared minus 2 times 5 is 25 minus 10, which is also 15. And they should have the same y value. And then we can integrate this. Now, I will point out, still 2 minutes, that you could have done this, or you could have figured out, sorry, let me back up. People usually ask the question, if I give them enough space to ask it, how do you know which function's on top without graphing? Because if you graph it, sure, it should be clear. Like clearly the y equals 3x is the bigger function here. But if we didn't graph it, how do you know which one's on top? Well, these two functions intersect when x is 0, when x is 5. And between those 2 points of intersection, only one function can be on top. Because if that wasn't the case, then they'd have to intersect again. So the way you can tell which one's going to be on top is pick any value between 0 and 5. I'm going to pick 1. Plug it into both functions. You plug in 1 here. If x is 1, what do you get for y? 3. You plug in 1 here. What do you get for y? You get 1 minus 2, which is negative 1. So since the y value is bigger here, that's the bigger function over the interval. That's how we know that y equals 3x is the larger function. And then the rest of this is the usual kind of definite interval stuff. You have the integral from 0 to 5 of 3x minus 2x is 5x minus x squared. You would anti-differentiate. You would get 5x squared over 2 minus x cubed over 3 from 0 to 5. You'd plug in, you get 5 times 5 squared, which is 125 over 2, minus 5 cubed, which is also 125 over 3, minus 0, which ends up being, I don't know, 125 times 1/2 minus 1/3 is 125 over 6. So I'm out of time. We'll talk more about area between curves on Thursday, as well as average value. And yeah, I'll just point out average value is super easy. If you know how to find the area under a curve, so I'll just say the average value of this function or of the difference of these functions, you would just take your integral and then divide by 5 in this case, because that's the length of the interval. So average value is just area divided by how long your interval is.